Hello, everyone, and welcome to a new session of engineering or basic engineering. If you remember last time or last two sessions, we were talking about moments or torques. Just to refresh your memory, we said that a moment of a force is its tendency to produce rotation, and the rotation is always about an axis. And this axis is perpendicular to the plane in which the force and the position vector are located. So if they are in the xy plane, the moment would be about the y, about the z, either positive, meaning going up if the rotation is counterclockwise, and going down, or negative if the rotation is clockwise. And then we extended that to the case of 3D, and we learned how to use matrices to find, or the determinants to find the moment in vector form. So we also said, or maybe that was implicit, I didn't make it clear, that suppose I have an axis here, O, and if I have a force, let's say any force, like a force like that, if we know that the rotation is counterclockwise, so if we don't need to use determinants, we can simply draw a line perpendicular to from the axis to the line of the force, and we call that D, and we say the moment here, moment as a magnitude equals F times D. Okay? That we know that. What does that mean? That means that if the force gets closer, closer, closer until it passes through that axis, it won't be producing moment, right? A force cannot rotate. Remember, that's what we did when we looked at the particle equilibrium. We said if all the forces intersect at a point, why would I care about rotation? There is no rotation. You can't rotate an object if you apply forces from all directions to that point. If some of the forces can move it along the X or the Y or somewhere in any angle, but it cannot rotate the object, the object would stay, with the same orientation. When else can't a force produce rotation? So we said if it passes through the axis, notice this is an axis of rotation. Okay, so I cannot rotate the paper. So this paper, if I want to rotate it about this pen, I apply a force not passing through the pen. You see, the paper rotates. But if I start to push exactly along this line, yes, the paper would move, but it will not rotate. When else? Very simple. If the force I apply is parallel to the axis, it cannot rotate about the axis, cannot produce a rotation like that if I push down on the paper at any point. So two things you have to remember. A force cannot produce a moment about an axis if it passes through this axis or if it's parallel to the axis. It's like, that's what we showed. Today we are going to look at something slightly different. What if the forces come in pairs, two equal, opposite, and non-collinear forces? We call that a couple. So what are couples? Suppose I have this axis and I apply the force like that, but then let's see this distance. So if that distance is almost 6 centimeters, so let's extend this line another 6 centimeters and then take a force parallel to that force, but applied in this direction. So the distance between the two forces is 2d. Now someone can say, yeah, this force rotates about O, produce a moment equals to Fd, and this one is rotating also counterclockwise. So if this is F, the purple F, and this is the green F, the purple F is also producing F times D. So the total moment would be 2FD, meaning the magnitude of either force times the perpendicular distance between them. That is called a couple. But couples, why do we call them couples? Yes, because they are two, of course. But what the, that makes them different from the regular moments we learned about? Think about it. What's the difference between a regular moment or torque and the moment of a couple? Both are moments, right? And of course the magnitude is different because here the distance is twice d, but I could apply it at O, and that would be a d, F times d, and this would be zero, but that's not the issue. What is the main difference between them? If you remember what we did earlier when we were discussing vectors, we were saying uh, a vector is a free vector, meaning I can slide it along its line of action, I can move it parallel to itself, as long as I don't change the magnitude and the orientation of it, it stays the same. And then we had a word of caution. I told you, be careful. Forces are not free vectors. Why? Because if a force, yes, it has a magnitude, it has a direction, but it has a specific line of action. I cannot move it from that line of action to anywhere else. So forces as well as moments. Notice the moment about O has a unique direction, and if I take the moment about any other point, I get a different value. So I cannot, it's not a free moment. It's not a free vector. It's a specific vector, right? At each point, the magnitude of the moment is different. But for the couple, couples are free vectors. What do you mean? I mean that if I take the moment of this couple about this point, I get 2FD. Let's try to take it about this point. I get F times 2D plus 0 because this one passes through that, so I get 2FD. If I try to take it about this point, this force doesn't produce moment, it's 0, but this one is F times 2D. Huh. If I take a point out here at a distance, say, of x, then the moment about this point, let's call it O prime, the sum of the moments about O prime would be F is rotating counterclockwise, so F times 2D plus x. But this guy is rotating clockwise, so it's the negative moment, F times x. So this is 2df plus fx minus fx. It's still 2df. So it doesn't matter where you calculate the moment. This is a free moment. You can place it here, you can place it here, you can place it anywhere, and it's always going to be parallel. So it's going up, it's going up at this location, at this location, at this point, at that point, anywhere in the plane. So that's the main difference between a couple and just a regular moment. Okay, makes sense? Now, we'll see how we are going to describe it, or how are we going to show it. Notice that I still could use a determinant to find the couple, but now I have the freedom of choosing any point I want. I can pick this point and find the position vectors, but if I'm smart enough, I'm going to pick a point along the line of action of one of the forces, even this point, that point, it doesn't matter. Why? Because as you saw, if I try to find the moment about this axis, this force will not be producing moment, only this one. So I can draw a line from here to there, that's the position vector, and R cross F would give me the couple, the moment of the couple. Let's take examples. I think in 2D it's pretty straightforward. I don't know. brought like two problems. They are in 3D and they are easy. And then after that, maybe we can have another session where we take forces that are not necessarily parallel to one of the axes. The first thing, when I look at this example, okay, I have two forces, 15 up, 15 down, so that's a couple because they are parallel to each other. So that's a couple right there. First thing you notice is that these two forces are parallel to the z-axis, so they won't produce z moment. I want you first to visualize. We'll do it mathematically, but first, how can you solve a problem without doing the determinants? Of course, they will ask you to show your work, and of course, you have to show how you did it. But I want you to get the sense. I will show you how I would solve this problem. I'm not a student, so nobody will tell me, oh, you can solve it without showing me step by step, right? So I have this freedom over you, right? But I was going to tell you the following. I'm going to look at 15 and 15. Notice this one is 300 millimeter from the y-axis, and this is only 200. So they will be producing a moment about the y. Notice if they were at the same distance, so if that was a 200, you will see this one is rotating clockwise about the y, 15 millimeter times zero point 0.2, and this one will be going counterclockwise, producing a positive moment. And if the distance is the same, so they won't be producing moments about the y. And you said, did you see what I want to say? What I want to say, I told you a couple is a free moment. So if this was, let's assume it's 200. I can take these two forces and move them parallel to their line of action until they are on the y. Why am I allowed to do that? Yes, because it's a free moment. So meaning I am free as long as I don't change the sense or the orientation or the magnitude of the forces, I can move them parallel to themselves. So they wouldn't be producing a moment about the y, but now they are. The distance between them is what counts, not between them and the axis. I hope you understand what I'm saying. The distance between this force and that force, one of them is going down 200 millimeter from the y, one of them is going up 300 millimeter from the y. So this one is further away, right? So the distance between these two forces on the x-axis is 100 millimeter or 0.1 meter, right? 100 millimeter. And eventually it's rotating clockwise about the y because the further away is the one going up. And this is the positive y. So I look at the y-axis from here and I see the force coming from my left and turning clockwise. So this moment would be negative 15 times 0.1 meter. And is a j because it's rotating about the y. We said they are parallel to the z, so they don't produce moment about the z. But how about the x? How far away from each other they are? They are 300 millimeter away. And these two produce counterclockwise rotation about the x-axis. Yes, this is clockwise and this is counterclockwise, but this is the bigger because it's further, and the difference 300. So I would say positive 15 times zero point 0.3 I. And here is the answer. That is the moment. And you say moment about which point? No, there is no such thing about which point. It's about any axis in the plane, about any point in the plane. It's the same moment regardless. It's a free moment. And I say Newton meter. Now, I said we can solve this Also, if you saw or understood what we did here, you're done. You already know everything about couples. However, we are going to say, okay, I have to show my work, so let me work it out. I'm going to say the moment. I can pick a point, okay? I can pick a point. If I'm clever enough, I will take the moment about A or about B. I don't care, okay? So let's say I take the moment about point A. Here is the moment. This, I don't care about this force because it's passing through A. I'm going to draw a vector going from where I'm taking the moment. Notice, please, this is a very common mistake. My position vector would be RAB, not RBA. RAB. This point, the first letter has to match this letter. If you do that, if you keep noticing that, you will never go wrong. So, I, J, K, I, J. The force is 15K, right? I'm sorry, the R first. I'm going to write the force. I prefer to write the force first. 1500. And then going from A to B, I'm going to move. This is 200 and this is 300. So I'm going to move 100 along the X, 0.1 meter along the X. I'm going to move from 300 to 600, meaning I'm going to move 300 along the Y. But I'm not moving in the Z at all. So 0, 0.1, 0.3. Now, I do the moment. So I say equals. I open parentheses or two pairs of parentheses minus two pairs of parentheses and close the bracket. 15 times 0.3 or 0.45 I. 0J, 0K. So plus 0 plus 0, or you can leave them blank. In the opposite direction, 0I, 15 times 0.1 is 0.15J, positive, so plus 0.15J, 0K, plus 0 Newton meter. So the moment would be 0.45 I minus 0.15 J Newton meter. Exactly the same. 15 times 0.3 is 0.45. I'm sorry, 4.5. Why did I say? I'm so sorry. This is 4.5. And this is 1.5. Oh my God. I can't multiply even. So 4.5 I and 1.5 J. Now, so you see, we can do it even by just by looking when the forces are either parallel to the X, Y, or Z. Even if they are inclined, I can break them into forces parallel to the X, Y, and Z. As I mentioned last time, sometimes we tell you, can you find the perpendicular distance between the forces? Yes, I can do it geometrically. I know that this distance, as we said, is 0.3 and this distance is 0.1. So distance equals the square root of 0.3 square plus 0.1 square. It's that simple, right? So it's the square root of 0.09 plus 0.01 equals the square root of 0.1. But at the same moment, at the same time, I can say the distance equal the magnitude of the moment, which is the moment of the couple, divided by the magnitude of the force. And the forces are 15. What is the magnitude of the moment? The calculator? It's the I'm sorry, it's the square root of 4.5 square plus 1.5 square. And the magnitude of the force is 15. Divided by 15, I get 0.316. What is the square root of 0.1? 0.316. So you see, we can check even our answer and know that we get the same result. Let's take another example. This is similar. Oh my God, it printed the same one. That's weird. Oh my God. Okay, let me then try to give you another problem. Make up a problem. Let's say I have a beam that looks like that, whatever. Let's make that 2 meters. Let's make that 1 meter. And then I have a force at this point, let's call it A, going in 3D. Let's say it's 100I minus 50J plus 200K Newton. And then maybe at this point, so these are in the XY plane. And here I have another force parallel and equal. So it's negative 100I plus 50J minus 200K Newton. And I want to find the couple produced or the moment produced by this couple. Very simple, right? Here is my X, Y, and Z. So in this case, of course, I will use determinants. I would say the moment. Again, I can pick point A or point B. It doesn't matter. Or even the origin. But that would be stupid. Sorry. Because I will have to find the moment of this force and the moment of that force and then add them up. But if I take the moment about A or B, I just need the moment of one force, right? So let's take it about B since last time we did it at A. Meaning my position vector, I cannot overemphasize that because no matter how many times I say that, I had students who consistently, when they take the moment about B, they say, oh, it's this force, so I use this for. So your position vector always starts where you are taking moment, always ends anywhere along the line of action of the force. Okay? So point if I end up at A, that's the easiest because it's only 1 meter in the Z direction, assuming that this was the X, and then I went down. So it looks like that. This beam is looking like that. At this force, there is a force, and at that point, there is a parallel and equal force. So this is point B is 1 meter below A. So in this case, to take the couple, I will take the moment about point B. So I would say I, J, K, I, J. The force down here will be this force. Okay? If I use the moment about, I'm sorry, I'm taking the moment about B, so it's that force. So the force at A. If I take the moment about A, I use this force. So the force is 100 because it's the top force, minus 50, positive 200, 150. And the position vector is 0, 0, 1. It's just one along the z-axis. So 0, 0, 1, 0, 0. Notice that we could have taken 50 as a common factor outside and write this as 2, negative 1, 4, 2, negative 1. Sometimes, especially if here I had like 2.5 and 1.25 and whatever, it might have been easier. But in this case, really, it's only one non-zero entry, so it's pretty straightforward. I can say the moment at B equals I go in this direction, 0I, 100J, and of course 0K. Then I go in this direction, negative 50I, 0J, 0K. So it's 100J plus 50I. So usually we write the I first, Newton meter. And I can find the perpendicular distance between them, between the line of action of this force and the line of action of that force, by taking the magnitude of that and finding the magnitude of the force, meaning the perpendicular distance equals the magnitude of the moment over the magnitude of the force. The magnitude of the moment is the square root of 100 square plus 50 square. The magnitude of the force is the square root of 100 square plus 50 square plus 200 square. And when I divide this by that, I get 0.488 meter. So basically, again, this was just I wanted to give you a force in 3D um, and to find the moment, but the idea is the same. However, as we said, this moment um, is like a free moment. I cannot say it's only MB. If you take MA, you will get the same result. If you take MO, you get the same result. If you take M about any axis, you get the same result. Okay, that's the difference between a regular moment and the moment of a couple. I hope this was clear. Hope you benefited from it. I may have another session where I will try to find more not complicated but better examples to go over. If you have any comments, again, as usual, I encourage you to leave a comment and I definitely will come back to you as soon as I can. Thanks and have a great day.